Let's talk about pointers and relational operators here. So just remember, what is a pointer? A pointer stores memory address. A memory address is an integer, right? Because it is always represented as a hex, right? Hexadecimal is the same as an integer. So when you put an integer inside an if clause here, right? So let's say if there's an integer here, this entire integer represents an expression that evaluates to a true or false, right? So in computer science, 0 is false, right? All others, basically any numbers, are typically true, right? So this is saying that if pointer has a value in it, this if, right, will return, this entire condition will return a true, right? If not, right, it will be false. So null is an important initializer, a value that you would always use to initialize your pointer with, right? NUL actually is 0. This is a macro that has a value of 0 in it. Now, effective C++ 11, again, we're talking about C++ here. What happens is they introduce this type safe pointer called NULL, right? PTR, okay? NULL PTR is lowercase, whereas null, these are uppercases here. I guess here we're using null to represent this. This is a long form, this is a short form. A lot of times there's really no preference as to whether you should be using long form or short form, they are equivalents, right? So this is saying if pointer is null, right? Or the same as using if, right? Exclamation PTR. Or if pointer is not null, right? Or if pointer has something in it, which is very much understood in the industry. Now, this is a pictorial representation of a solution that in C or even C++, representing the use of array and 3 other variables to keep track of the smallest elements, which is 8 here, out of all of these elements from beginning to end. So we have actually 4 pointers. ARY is the name of the array. We have P small, right? This is a temporary placeholder. We use this temporary placeholder to keep track of the all-time smallest. So just looking at using P smallest as a global variable that tracks the all-time smallest as we use P walk, right? This pointer to walk through every single element starting with, right, 32 and then 8 and then 14, right? So there's iteration number 1, number 2, iteration number 3, and number 4, right? So there's actually 4 iterations for us to get there. There's also a plast. So plast function is really for p walk to stop, right, at plast, knowing that p walk is already at the end, because you don't, once you pass 20, right, you don't want to keep going because then you'd be writing into someone else's memory addresses. So let's look at after initialization. We know that p walk is initialized to AR1 1, right? So ARY 1, right? Whereas p small, right, is ARY, right, 0. So you can do the comparisons there and see if you know, p walk is landing on the all-time smallest. If that's the case, then p small, right, is going to be pointing right from 32 to 8 now, because 8 is the smallest after the first iterations. And then you have second iteration that involves p walk, just keep going, right? Like I said, right, until p walks all the way at the end at last. So meanwhile, while p walk continues away, p small, right, will keep track of the all-time smallest. So treating this as a global variable that changes at any given iteration. Iteration continues, p at the 4th iteration reaches the end. When p walk equals p last, you don't want to have another 5th iteration, because that would entail p walk getting out of the boundary. This will be pretty bad. So the code, this is a pseudocode, right? So p last equals to the beginning address of ARY plus array size. We don't know what this size is, but let's say if we know that this one, 1, 2, 3, 4, 5, there's only 5 elements in there, minus 1. So p last, remember, is the beginning address plus the array size minus 1. Why is that? Well, remember, array indexing starts with 0, right? So when you have array size minus 1, this basically puts you into the array index mode. and you want ARY as the beginning 0 plus this amount, right, to get to the very last. So this actually gives you, let's say this is 0, 1, 2, 3, 4. So how many elements do we have? 5, right? So 5 minus 1 is 4, and 0 plus 4, this will actually gives you the very element being array 4, right? So this is the address of the last p last, or the elements of the array. So if you do this in for loop, you said p small equals ARY, and this is all in memory, right? Remember, memory address is an integer, right? So this is saying, this ps, right? This p small equals ARY. That gives you the initialization. And then you said, actually, the other initialization you have is p walk equals ARY plus 1, right? So at this point, you're able to set basically 2 variables at the same time. And then you begin your conditionals and increments. Your conditional saying p walk is less than or equal to p last. As long as p walk is less than or equal to p last. Remember, this is assuming that the memory address actually goes up this way. Like I said, in some machines, it depends on the Indianness of the machine. Memory address doesn't always go up. Sometimes it goes down. But using this method, we can say that p walk is less than or equal to p last, and then we keep the iteration going. P walk, this very last increment, this is using what we call pointer arithmetic, right? So it's very important that we keep tab of p walk, right? We want to make sure that p walk is less than or equal to p last, because once you go beyond, right, 4 into the 5th or 6th location of ARY, you're out of the boundary. So then we keep track of the all-time smallest, right? Basically doing a comparison by dereferencing, p walk. If the value where p walk is pointing to is less than the all-time, minimum, then we want to set all-time minimum to be the pointer that is pointing to p walk at the time. So we basically just use these 4 pointers throughout. Only p small and p walk are moving, but ARY and p last are fixed, right? One pointing to the beginning, the other one pointing to the end. This is another C example. We set the array size to 10. So there's actually 10 elements here. And the name of the array is called ARY. There are 2 pointers. One of them is the walk one. So expect that this p walk to go from the index 0 all the way through, right, to index, right, where this pn actually points to. So this is pn. So we actually have 3 pointers, right? The first one, second one, and third one. And we know the size of the array is 10. That's what happens here. So now let's print the array forward. So from line 20 through 24 is how we print the array values, right? There are 10 of them, one at a time, from beginning of the array, ARY, to the end of the array, one at a time. So this uses a pointer arithmetic and also the directions, namely dereferencing, to carry out this thing. Let's look at this for loop right here. We know max size is 10, right? So ARY plus 10 just gives you PN here, and this PN, this is actually tricky, right? If you say this is -1, then you want to use less than or equal to, right? But we get rid of the -1, so you can actually do some math here. Then as long as P walk is less than P end, we do P walk plus plus. We also want to print this out, right? What if this is 1 at a time? So this actually gives you a way forward here. Let's do it backwards here, right? Printing the array backwards involves setting, right, P walk all the way at the Pn -1. Why? Array indexing is size -1, right? So this is all necessary. And then we want to do P walk minus minus. So this is pointer, right? Arithmetics. Just like here, this is pointer arithmetics here. But every time we decrement, we want to make sure that P walk, right, ends at ARY, which is ARY 0 locations. We don't want this to get into the native location because that would entail touching someone else's memory address. So when we dereference that pointer, we get back that value. This allows us to print, all of the elements backward 1 at a time, from 10 all the way through 1.